Hi, my name is Georg. I'm a system engineer at Bitlismen company. Today I'm going to demonstrate our product NETSimulator. The NETSimulator simulates real high voltage and high current signals. It can be used in university labs, vocational colleges and research universities as a simulator of voltage and current transformers, based on which various labs can be created. Another application of NETSimulator is the testing of various power metering devices and microprocessor-based relays. For this case, NETSimulator API should be used for loopback acquisition and testing. NETSimulator helps to create different labs and explore the power and energy basics, develop control algorithms for different assets of power infrastructure, investigate the emergencies and their effect on power network, test and calibrate power meters, analyzers and protection devices. NETSimulator consists of a NETSimulator software, NETSimulator voltage adapter with 3 voltage channels, NETSimulator current adapter with 4 current channels. The product comes with many options: NETSimulator software only, NETSimulator software with 1 voltage adapter, NETSimulator software with 2 voltage adapters for double 3-phase network simulation, NETSimulator software with 1 current adapter, NETSimulator software with 2 current adapters for double 3-phase network simulation, NETSimulator software with 1 voltage and 1 current adapter for full 3-phase network simulation, NETSimulator software with 2 voltage and 2 current adapters for full double 3-phase network simulation. Today I'm going to demonstrate the option with NETSimulator software with 1 voltage and 1 current adapters for full 3-phase network simulation. First, let's have a look at the software. The software comes with 3 licenses, one for 3 voltage and 4 current channels, the second for 6 voltage and 8 current channels, and the third one including an API for custom simulation algorithms and test environment development. As you can see, the software has self-descriptive and user-friendly interface. It allows manipulating with voltage and current amplitude levels, phase shifts, frequencies, and harmonics, up to 64th order. The waveform chart shows the simulated signals, and the vector diagram plots the vectors of the simulated signals. Now let's have a look at the voltage adapter. The input accepts 7 volt AC or DC signal, and the output ranges up to 220 volt AC or DC. The adapter converts the input low voltage to high voltage signal. The conversion is done transparently, meaning the high voltage signal will replicate the low voltage signal shape and spectral band up to 64th harmonics within 1% error. The voltage adapter is intended to be used only with measuring devices which have high input impedance. This means the output of the adapter cannot be connected to a load. Now let's look at the current adapter. Here as well, the input signal ranges within 7 volt AC or DC signal, and the output ranges up to 5 ampere AC or DC. This adapter converts the input low voltage to high current signal, acting like a current source. It will replicate the low voltage signal shape and spectral band up to 64th harmonics within 0.5% error. For detailed specifications, please refer to datasheets. Now, when we have a general idea about the system, let's go to the demonstration part. Firstly, we need to power up the adapters and connect the input and output cables. The black BNC cables are used for input signals. The other end of this cable should be connected to the analog output module of PXI. The banana cables are used for output signals. The other end should be connected to our PQA, which we will use as a measuring device. In addition, we will use another measuring device, an oscilloscope. Now let's go to the software and simulate real voltage and current signals. Let's start the simulation with default parameters without any harmonics. and see how accurately the signals are generated from the adapters. On the chart we see the signals generated and the vectors on the vector diagram. As you have noticed, in order to have current signals, we are simulating the load. We are able to simulate fully resistive, capacitive and inductive loads and also mixed loads. Using the voltage signals and loads in the ohms law, we get the current signals. Now let's go to the PQA interface and see what we are measuring. As you can see, the measured and simulated signals are identical in shape, of course within 1% and 0.5% error accordingly. Let's see the other related measurements, like RMS values, the frequencies, the phase shifts, and the harmonics. As you can see from the harmonic spectrum, we have only the fundamental harmonic and the remaining harmonics are very near to zero. Now let's use the NI5133 high-speed oscilloscope. For that, I will disconnect our PQA and connect the oscilloscope. I'm opening the user interface of the oscilloscope and running the simulation. As you can see, the signals are replicated accurately within specified accuracy ranges, and from the harmonic spectrum we also can see that we have only the fundamental harmonics and the remaining harmonics on the remaining frequency band are near to zero. On the first channel we have the voltage signals, and on the second channel we have the current signal. Now I will manipulate with remaining simulation parameters and compare them with measured values. Let's see. Here I have split the monitor into two parts in order to view the simulated and measured signals on the same screen. Hope you enjoyed the video. For more information, contact us directly or visit our website on bitlismen.com. Please subscribe to our YouTube channel and check our other products. Thank you for watching.